Hi, my name is Arya Karnik, and I'm working with Dr. Joshua Bittle in the Department of Mechanical Engineering on implementing priority traffic light algorithms in the real world. Quick presentation outline, I'll be going over the project background, overall objectives for the project, the algorithm overview that we're actually using, real world implementation, system components, and then finally, I'll dive into the future implementation and work of this project. Starting off with an overview of signal control, it's important when we talk about traffic to actually understand what signal control means and the phasing behind it. So we talk about phase definitions, we're actually talking about the numbers associated with different turn elements. Looking at left turns, right turns, we're also looking at straight turns, right? Or sorry, straight lines across an intersection. So straight right, straight left, straight through the middle of the intersection. And all of these phases together combine to be a cycle, right, when we're looking at an intersection. So there's three main types of signal phase controls. We have conventional fixed time, which is a phase on a timer. So this is as simple as the name defines it as. When you come up to a signal, you're waiting in a cycle, right? A fixed time signal, maybe 10 seconds, 5 seconds. And a great anecdote to think about this is like when you come up to a light and it's a red light, but the crossing street is green and there's no traffic there. And you're waiting, and it finally turns green, right? That is an example of a timer-based system where we're just waiting to see when the next timer hits and then we switch to what the next phase should be. We also have semi-actuated. So this one's really interesting, right? Because when we look at the main road priority, that essentially means that the main road in a major intersection will always have the priority, essentially meaning that if there's no traffic on the side roads, it'll always be green, right? And then we're detecting on these side roads to see and understand, hey, is there traffic there? Should we switch to that phase? Should we give them a right turn, left turn? Exactly, depending on the traffic, right? So it's really looking at keeping that main traffic flowing while understanding what the left turn and right turns look like. We also have fully actuated. So this is where every approach to an intersection actually has some sort of detection method, whether it's cameras, radars, or magnetic coils underneath the traffic. However, the main issue with this is that it's limited to the vehicles at the intersection, right? It does not have the awareness to understand what traffic's flowing into the network at that intersection point. And so what we're trying to accomplish here is actually implement an algorithm where we're giving these fully actuated signals and systems the full broad scope of the network to actually help improve traffic through an intersection node. So our main objectives here, we want to validate simulation results in the real world and demonstrate the viability of the truck speed priority approach, which is the main one that we found had the most improvement in our simulation results. And as this one, as the name defines itself as, what we're trying to prioritize is trucks, right? When we look at the weight of trucks in the algorithm, when I say weights, I'm talking about the priority weight they have at the intersection. It's really simple to think about as with the term of kinetic energy. Right? Trucks have more kinetic energy, right? It takes more energy for them to stop, it takes more energy for them to accelerate, and that's when you can save the most fuel consumption if we just let trucks go through the intersection. So what we're trying to do is actually implement this in the real world and then propose improvements to this algorithm, right? Even though we validated it in simulation work, we want to see in the real world, hey, how does it work? Does it work well? Is it going to be successful? And then from then synthesize results for external stakeholders, right? Understanding, hey, can we actually take these algorithms and take these approaches and put them in situations where there are more trucks, right? We have tons of infrastructure and industrial work going on in Tuscaloosa, right, where we have a lot of trucks. And if we can implement those in those situations, then we should hopefully see better fuel consumption throughout a network. So a quick overview of the algorithm we're using. So it's a genetic algorithm. So this graph on the screen here, what we're looking at is actually what we did in simulation, right? So we have a genetic algorithm that's optimizing these various different parameters to understand how we can best, save fuel at a network point. So when we look at the traffic simulator interface itself, we're actually basically assigning the next green phase based upon the dynamically changing traffic at that intersection point. So this leads to a dynamic adjustment to traffic. And so this is an optimized weighted sum of different priority factors and metrics that then determine what phase we want to switch into. And from here on out, the whole ultimate goal, right, is to minimize the network-wide fuel consumption through these different dynamic adjustments of traffic, because every intersection is ultimately different. So where are we actually going to implement this in the real world? We're going to be at the Campus Drive and Peter Bryce Boulevard intersection, which is right next to the softball stadium on the northeast side of campus. So here, this is a really interesting intersection to look at, right? Because it's right off US 82 coming into campus, but it's also not a main intersection on campus, which is important, right? Because we don't want to go and actually implement something where it might not work as we expected. So we have enough traffic here, enough variety of traffic here with buses, with cars, where there's enough flow to see if our simulation works without too much disrupting traffic if things do not go the way we anticipate. How we're actually going to implement this real-world algorithm, we're going to be taking the live camera data from the intersection as well as the live radar data. This will be piped into the traffic signal controller that I mentioned previously, where we'll have our priority algorithm interjecting with the phase controller itself. So we'll be looking at the current phase and the next phase and understanding, hey, how can we take that next phase and implement to the current phase? So from here, the ultimate objective is to understand with our next phase and our current phase itself, can we make sure to emphasize that traffic is being flowed throughout the network efficiently? Because ultimately, if we can understand what traffic is coming into the network with the right awareness, we'll be able to then go from that step forward, right, and then turn on the correct phasing based on the traffic at the network node. As I mentioned previously, this campus drive in Peterborough Boulevard is actually a fully actuated system already, so the infrastructure is already there as well. So something nice that we'll be able to take advantage of is the fact that we have working radar and we have working camera data to work with. From that point onwards, however, we want to ensure that we can actually see if there's a bus coming all the way down, coming from North Lawn all the way through to that intersection, can we accurately get that fast enough to then we can actually implement that into our algorithm results. From here on, we're talking about the system components itself. So first, we have the Advantech MIC730 AI unit, which is a compact embedded system design. And this is great for our use case because, as I said, it's very small and it's very lightweight, so we can actually just easily put that in our signal controller box without having any effective worry about weight distribution or things along that line. It's also embedded with the NVIDIA Jetson platform, and this is a little bit of a buzzword here, but it has 32 TOPS, which is trillions of operation per second. This is really important because it allows us to deploy the real-time algorithm at the edge. And so what the edge means is we're actually doing our computing on site, right? One of the big things when we look at traffic is latency, right? We don't want to have to basically look at traffic and then send it back to a lab in Circ and then send a new phase out. Then traffics are going to be waiting there anyways. And we don't want to spend that cost because if we keep the red light for even 1 second too long, well then the bus is already slowing down or coming to a stop, as an example, well then we've already spent the cost, right, of that fuel. The fuel is gone, and then we're already have to spend it again if we turn it green for it to reaccelerate. So if we can get it on premises locally where we can ensure that the speed is going fast enough, right, then from their point onwards, we can ensure that we're actually accurately defining what we need to do at that phase before it's too late. We also have access to the radar firewall and firewall code. So I'd like to acknowledge Dr. Alexander Heinen in the Department of Civil Engineering for helping us work to get access to these firewalls so we can actually connect and start bench testing with this code that we're working on the Advantech unit itself. We're also using the Econolite EOS traffic signal controller, and this is a really interesting piece of software where we're actually able to see real-time vehicle calls at the traffic signal interface itself. This is really important for us because when we look at what vehicles are coming into the network itself, we understand and we can take away what vehicle calls are happening and what is supposed to happen, right? So something really important for us is validating the work we're doing to ensure that in the future, when we look back at this work, it makes sure that we actually saw the vehicles as they were supposed to be. So future work for us from here, as I mentioned previously, we want to deploy this completed system to a real intersection. So we want to take the system, all the stuff I just mentioned, and actually finally deploy it in the real world. We also want to track situational performance, right? It's very important whenever we look at these algorithms to ensure that even though it works in simulation, the real world is not perfect, right? We have to ensure that it's actually detecting correctly, it's making the right decisions correctly at the right times. We also then want to work to validate and iterate our algorithm performance. So that ties back into obviously situational performances, right? Not only do we want to make sure it works, but does it work at certain times, like game day, for example, right? Or certain high activity events where there's a lot more vehicle traffic, because we want to ensure that every person in the system is, has an opportunity to get a green light at the signal, right? Because no one wants to sit there and wait just because our algorithm keeps saying, okay, this car can go through, this car can go through, this car can go through. Well, what about that one car that needs to just get into campus, right? We need to make sure that it works for all situations at all times. Finally, we then want to expand this deployment to distributed nodes and then hopefully see the cascading effect of fuel consumption improvements across a network. This time I'd like to open up to any questions.
This, slide 4, it seems like at any intersection there's 81 different kinds of states you could be in, four points and then three ways to go each time. So I have a couple questions. One is, what if you threw a roundabout in there or something, some kind of variation? What is that going to do to some of the analysis you have when there may not even be a need for the same kind of traffic lights?
So you're saying a roundabout without any traffic signal lights, or one of those that are a controlled roundabout?
Well, tell me about both.
Yeah, for sure. So obviously when we're looking at a roundabout without any traffic signals, right, then the algorithm doesn't matter, right? Because ultimately when you have no signal control, right, the whole idea is that the traffic is being controlled by itself by the flow of traffic, and then ultimately yield signs come into effect there anyways. So at that point, it doesn't really matter. With controlled roundabouts, it'd be the same type of concept, right? Because essentially what we want to do is ensure that if a truck is coming into a roundabout, it has to slow down anyways. We want to make sure that it can pass through and keep, that preserve some of that kinetic energy throughout the system.
I just want to clarify, your work is more the algorithm applies to the traffic light itself.
Yes.
Is there any application, like if I wanted to do some kind of variation of the algorithm for autonomous control itself, where the cars are starting to communicate and know how to interact with each other?
Yeah, that's definitely a next step that we're looking at, right? Obviously with V2X, right, and understanding how vehicles can connect to these systems. Obviously, in the future, it'd be great to understand when the vehicle can ping even miles away that's coming to this intersection. But right now, our main focus is taking the technologies we have now and improving current infrastructure.
So I know that you said that the trucks have this increased weight in the algorithm. They have this higher kinetic energy per se. So how does this research kind of affect urban areas where there's really not many trucks you have to deal with, but there's a much larger concentration of these streetlights in these intersections?
Yeah, and I think that's a great example of what we're kind of talking about, right? Where we want to actually take this in the real world and understand, hey, does this algorithm still work even if we're not looking exactly at trucks, right? So I think the balance between those two is something that we'll definitely have to explore.
Could you explain how the algorithm handles edge cases for different traffic flow scenarios?
Yeah, that's a great question, right? I think it's ultimately the balance has to be, right, where we're looking at prioritizing the efficiency of the system without penalty to a single individual, right? And as the example I mentioned previously with one car waiting, we need to make sure that the whole efficiency of the system stays high, but that every vehicle has a chance to hit a green light. So that's an extremely important part and something we're really looking forward to. So.
For your project, when you're determining what is a truck, what are your parameters for that? Because obviously there's visual and you're using AI to get images, but with like cars changing continually to new models coming out, what are your parameters for trucks and for cars?
Yeah, so I'm really lucky that we're working with a really big team here on the Center of Advanced Vehicle Technologies group, right, where we have existing camera models and radar models. So one of our PhD students, Madi, he's been working a lot with that camera detection side. So I can't speak much to that specific side of the research. All I know is that when it gets into my algorithm, that we're fairly confident it's a truck, right? So it's something to definitely explore, though, when I talk about situational performance when we get out to the field. Is it actually a truck, right? And how does that actually affect the algorithm? So definitely something we'll be looking at.